All right, everyone, what's up? So today we're going to be talking about genetic imprinting, Prader-Willi, and Angelman's. And so I'm not going to lie, this is one of my favorite topics from FTM 1. And the reason why I like it so much is because literally everyone else hates it. They, for whatever reason, they just don't like it. They have a hard time understanding it. I did it first as well, but then once you get it, it's sort of cool because like it all kind of just makes sense. But the way that it's kind of just presented in class and the way it's kind of formatted doesn't really make sense. So basically, we're gonna break it down today, and we're gonna make it make sense so that you get it and you are ready to go for FTM 2 because it's gonna come back. It's gonna come back in the epigenetics section, and honestly, a lot of information from the epigenetics section should have been put into FTM 1 as far as like how the material was integrated, and for whatever reason it wasn't. So you know what? Today we're just going to learn it all. We're going to learn it all the way through, including the FTM 2 stuff. Don't be afraid of it. You're not going to see it probably in your lecture slides for FTM 1, but it will come back, and it's better to just like learn it now and understand it now, and then you won't be in the boat of people who hate it. You will actually like it because then you can explain it to all your friends and it'll make total sense, and like light bulbs will go off left and right. But to do that, you need to like kind of put the entire picture together, which isn't given to you right off the bat. So basically, let's go ahead and jump straight into things. And first of all, before we start, we have to address one thing. So imprinting. So what is imprinting? Okay, so when a gene is imprinted, basically what that means is the gene is silenced. That's it. It means that the gene is just turned off. So if it's genetically imprinted, the gene is turned off. So if it's the maternal copy or the paternal copy, whatever it is, if it's imprinted, it means that it's silenced, it's turned off, and the way you do that is through methylation. You'll talk more about this in epigenetics, cytogenetics, all that kind of stuff later on, but that's what you kind of need to know for FTM 1 is that if a gene is imprinted, that means it's turned off. So the next thing you kind of have to establish before moving any further with all of this is you kind of have to separate out the diseases from the genes themselves. So like Prader-Willi and Angelman's, they were kind of taught together, and I understand why they were taught together as far as like, you know, they're on the same chromosome, which is great, but like I guess it's because like they have the same like sort of patterns as far as like how the methylation and everything and like the silencing and whatnot work. But at the same time, they should have never been like shown in like the same like sort of graphic together as far as that's concerned, because they don't work together. They're separate entities, and how you get silencing and stuff are completely like separate from each other, and we're going to talk about them individually today, and it's going to make way more sense than probably in class, and we're just going to break it down, and it's going to work out pretty good. But in order to do that, let's go ahead and just give out the straight out definition. So Prader-Willi. Okay, so what is Prader-Willi, right? Prader-Willi is the absence of a functional SNRPN gene. So the SNRPN gene, that one, the SNRPN gene, I'm just going to call it that. It's the absence of a functional SNRPN gene. That's Prader-Willi. Excuse me. Angelman's, on the other hand, is the absence of a functional UBE3A gene. So the UB gene, it's an absence of the UB gene. That's Angelman's syndrome. So both of these genes, right, or both of these diseases can be caused by either one, a microdeletion, okay, and we're going to see that in a second, or two, uniparental disomy. So those are the two ways that you can get these diseases, and both of these genes as well are on chromosome 15, which we'll talk about as well in a second. All right, so those are the diseases, right? Prader-Willi, Angelman's, okay? Prader-Willi, absence of SNRPN. Angelman's, absence of UBE3A, okay? Now let's talk about the genes. SNRPN, all right? SNRPN is a maternally imprinted gene, okay? So what that means is that SNRPN, the gene itself, don't think about the disease right now. The gene itself, SNRPN, okay, is maternally imprinted. That means that the maternal copy, the copy that you, me, everyone else, your friends, whoever, got from their mom, the copy they got from their mom is going to be turned off. It's going to be silenced. Why? Because imprinting, genetic imprinting, means that the gene is silenced. So in the case of SNRPN, the maternal copy is silenced. That's it. That's all you got to know for that. In the case of UBE3A, the other gene that we're talking about, right? Don't think about the diseases right now. In the case of UBE3A, the paternal copy, meaning the copy that you, me, everyone else got from their dad, okay? That gene is paternally imprinted. So the paternal copy is going to be turned off, okay? So in both of these cases, however, the other copy in a person who does not have Prader-Willi or Angelman's or anything like that, the other copy is going to be turned on. So that means that in the case of SNRPN, your paternal copy is going to be turned on because it's only maternally imprinted. That means the mom's copy is the one that's turned off. It's not the dad's, right? And then the other way around for UBE3A is that since it's paternally imprinted, right, the maternal copy, it has nothing to do with that. The maternal copy is going to be turned on, or if you have a disease, it's not going to be turned on. So that's kind of how you have to think about this, right? So you have to separate out the diseases from the genes, and now after you get that straightened out, then you can put them together and figure out what's going on. All right. So now that we're clear with that, if you need to listen back to that, I probably would before we go forward, because now we're going to jump straight into the diseases and see how it works with these imprinting things that are going on. Okay. So the first disease that we're going to talk about is going to be Prader-Willi. All right. So what did we just say Prader-Willi was? We just said that Prader-Willi, by definition, we're going to call it the lack of a functional SNRPN gene, right? So that means that someone with Prader-Willi has no SNRPN. That's functional, no functional SNRPN. How the SNRPN became non-functional, that can vary. That can vary depending on either the microdeletion route or the uniparental disomy, and we're going to go over both of those. So the first way you can get this situation is with either a uniparental disomy, or the first way we're going to do is going to be a microdeletion. A microdeletion is the first one we're going to talk about, because it's easier to understand. So basically in the case of a microdeletion, this is what's going to happen. You're going to have a child, all right, who presents with Prader-Willi syndrome. And this child is going to have 2 chromosomes, as we all do, right? We're going to have 2 copies of each chromosome. And we're talking right now about chromosome 15, right? So they're going to have 2 copies of chromosome 15. One copy is going to be from their mom. It's going to be the maternal copy. And the other copy is going to be from their dad. It's going to be the paternal copy. Okay? So what did we say about SNRPN, right? We said that SNRPN was a maternally imprinted gene, correct? Which means that the maternal copy of SNRPN is going to be silenced in every individual, okay? So this means that you, me, your friends, whoever, every individual, the maternal copy of SNRPN is going to be silenced, which means that it's going to be methylated. So right there, we're showing this methylation. This means that this copy is silenced. It is turned off. It's contributing nothing to the SNRPN gene. It's not active. The paternal copy, however, is going to be an active version of SNRPN. Right? So the paternal copy is going to be active. However, if you have someone who has a microdeletion, right? So they inherited a copy with a microdeletion. What basically that means is that the paternal copy is also non-functional. So then in this person, if the maternal copy is non-functional because of the normal imprinting that happened that silenced the gene, right? And the paternal copy is non-functional because of the microdeletion that induced it to become non-functional. You end up with a person that has no SNRPN. And what did we just say no SNRPN was? No SNRPN equals Prader-Willi's disease. So that's basically what happens here. Right? Easy enough to understand? Okay, that's a simple one, all right? So that's the easy one, and then now we're going to move on to the harder of the two concepts. It's still not too bad, but the harder of the two concepts, which is going to be the uniparental disomy. Okay. So basically this is what's happening here. So in the uniparental disomy, Okay, so in the uniparental disomy, basically what you're getting is a child that also has no functional SNRPN. But the way that they get the lack of functional SNRPN is through a different route. This time what's happening is you are actually inheriting two copies from the same parent, and both copies are turned off. That means that they're both silenced. That means that they are both imprinted, right? So how can this happen? All right, well, in order to figure it out, we have to go a generation back. And this is kind of where the FTM1 and the FTM2 lines kind of blur for this whole topic. And you kind of have to go into FTM2 to understand what's going on in this part of it, which is heavily like on epigenetics and stuff like that. It should have probably been taught like this to begin with, but we're going to go ahead and explain it this way. It's going to make way more sense. Okay, so let's look at this kid, right? This child, same child, except this time let's just say that this microdeletion didn't happen. We're going to look at the same child with this result, though, okay? So this child has two parents, right? So he's going to have a mom and a dad, okay? So the mom of this child is going to have two copies of the gene, right? The dad of this child is also going to have two copies of this gene. So basically what's happening here, and we're just going to abbreviate SNRPN as S. So this video isn't like 30 minutes long. So the mom and the dad are each going to have two copies of the gene, correct? So here's the thing. The mom and the dad are also each going to have a maternal and a paternal copy of the gene that they inherited from their parents, right? So you got to go a couple generations back for this to kind of make sense, right? So they each have a maternal and a paternal copy. And as we said, for every individual, the SNRPN gene, right, is maternally imprinted. So you, me, your friend, your mom, your girlfriend, your boyfriend, whoever, every person, the maternal copy is going to be imprinted, which means that it's going to be turned off. Regardless of if they're male or female, the maternal copy is always going to be turned off, okay? Until that individual makes their own gametes, okay? And this is when things change. Because when this individual makes their own gametes, now let's think about what's happening, okay? Let's take a step back and think about what's happening, okay? So, this person, this mom, had a maternal copy and a paternal copy, right? Okay? So there's the maternal copy, there's a paternal copy, and the maternal copy is turned off. Because that's just regularly what happens, okay? But when this person becomes a mom, meaning that this person makes their own gametes, then all of her copies are all going to be imprinted. They're all going to be turned off. Now, why is that? Well, that's because this person is now a mom, which means that they are now causing the maternal imprinting that we've been seeing all along. Because basically what's happening is when they create their gametes, all of their gametes are going to be silenced and basically they're going to be silenced because they are maternally imprinting their genes for the next generation, because the SNRPN gene is maternally imprinted. Make sense? Yeah, so you kind of have to like think about it. It's like, oh yeah, wait, like that's where it's coming from. So basically what's happening here is that whenever she makes her genes, they're going to both be maternally imprinted. Now what about the dad? Okay, well in the case of the dad, what's going to happen is basically he is going to, whenever he makes his gametes, they're all going to be turned on, right? Because the SNRPN gene is not, in any case, it is in no way is the SNRPN gene ever paternally imprinted. So basically when the gametes in the dad are made, the imprintation or whatever it's called, it's probably, I don't know if that's what it's called, but it's taken off. And all of these genes are made active. So this is what happens in uniparental disomy. Like, all right, so let me show you what happens here. So in uniparental disomy, basically what you get is you get a kid who has 2 copies from the mom, okay? And 1 copy from the dad, and they end up with 3 copies of the SNRPN gene. And you might say 2, but we'll get to it in a second. Let's just take a look at this. They have 3 copies of the SNRPN gene. However, of the 3 copies, 2 of them are maternal copies, and 1 of them is a paternal copy. And the 2 maternal copies are going to be turned off, while the paternal copy is going to be turned on. But here's the thing. Trisomy 15 is not compatible with life, because in this case you have a trisomy situation and it's not compatible with life. In fact, most trisomies are not compatible with life. Only chromosomes that have like very, very little genetic material will you see it be compatible with life. So basically what's going to happen here is a situation called trisomy rescue, in which the paternal copy is kicked out of the gamete as a whole. And what you're left with is a child with 2 maternal copies of this SNRPN gene. But if you look at these 2 maternal copies, what do you see about them? They're both imprinted. They're both methylated. Means that they're both silenced. And what that means is that this kid has no SNRPN gene. SNRPN. And what did we say no SNRPN equates to? No SNRPN equates to Prader-Willi's. That's it. So what we were able to see from this situation was we were able to see 2 different situations in which we had a child with Prader-Willi. And basically what's happening is you had either the first situation where you had a microdeletion and you basically lost the extra gene due to a microdeletion and you got no copies. And then you had one where you had a uniparental disomy in which you basically ended up with 2 maternal copies which are both imprinted. That's the entire principle of that. This is probably more in depth than you went to in class. And honestly, all you have to do for Angelman's is you just put in the UBE3 and just remember that Angelman's is paternally imprinted. Same principles apply. Whenever the dad in the Angelman situation, whenever he makes his gametes for the uniparental disomy, they're both going to be imprinted, and the mom's copies are all going to be turned on. Everything is just in reverse. That's it. You can easily solve these questions so fast if you just get this down. For the sake of not making this video too much longer, I'm going to skip over Angelman's for now. But if you have any questions about that, hit me up about that. But it's literally the same thing except in reverse. That's it. But yeah, that's the easiest way to do this. That's the easiest way to learn this, honestly. And it's probably way more conducive